Pluto was supposed to be a dead world. But when NASA pointed the James Webb Space Telescope at it, everything scientists thought they understood fell apart. Suddenly, Pluto looked alive. Ice shifting like seasons on Earth, its atmosphere leaking into space, and in a twist no one expected, that material drifting all the way to its moon Charon, painting it in Pluto's chemical fingerprint. Nothing like this happens anywhere else in the solar system, which is why the team studying it was stunned. Because the data doesn't just challenge old models, it breaks them. So, what exactly is happening on Pluto? And why are the universe's coldest interactions turning into one of astronomy's biggest mysteries? Pluto sits at the edge of our solar system, beyond Neptune, in a region called the Kuiper Belt. It's 2,372 kilometers across, making it the largest dwarf planet by volume. We've known about Pluto since 1930, when American astronomer Clyde Tombaugh first spotted it. For decades, we observed it from Earth and from telescopes in space, but we never got a close look. That changed on July 14th. NASA's New Horizons spacecraft flew past Pluto at a distance of just 11,095 kilometers. The images it sent back revealed a world that surprised everyone. Pluto has complex topography, basins, mountains, valleys. It has active geology, with glaciers made of nitrogen and methane. Its atmosphere is thin but chemically rich, containing nitrogen, methane, and carbon monoxide, and it's surrounded by an extensive haze. This haze forms through photochemistry. Solar ultraviolet light breaks apart nitrogen and methane molecules high in the atmosphere, and they recombine into tiny hydrocarbon particles. It's a process similar to what happens on Titan, Saturn's largest moon. Charon, by contrast, has no atmosphere. Its surface is more uniform, dominated by water ice mixed with ammonia-based compounds. But its polar regions are darker and redder than the rest of the surface. Scientists believe this is caused by methane molecules escaping from Pluto's atmosphere, getting trapped on Charon's poles, and being chemically transformed by sunlight. The New Horizons flyby gave us our closest view of this distant system, but it was just a snapshot, a brief moment in time as the spacecraft rushed past at over 50,000 kilometers per hour. We needed more. We needed to look longer. In the wake of the New Horizons observations, Xi Zhang published a paper in 2017. In it, he proposed something that sounded radical. He suggested that Pluto's atmosphere was dominated by haze particles, not gas molecules, but solid particles suspended high above the surface. And these particles were controlling the entire energy balance of Pluto's atmosphere. They would heat up when they absorbed sunlight. Then they would cool down by radiating that heat away as infrared energy, and this process would regulate the temperature of the entire atmosphere. If the haze was cooling Pluto's atmosphere by radiating heat, then it should be emitting strong mid-infrared radiation. And if we had a telescope powerful enough, we should be able to see it. That telescope arrived on Christmas Day, 2021. NASA launched the James Webb Space Telescope into space, and it began operations in the summer of 2022. JWST was designed to observe the universe at infrared wavelengths, with far greater sensitivity than any telescope before it. Zhang knew that JWST could test his hypothesis, and so a team of researchers, led by Tanguy Bertrand from the Paris Observatory, proposed observing Pluto with the telescope's MIRI instrument. MIRI stands for Mid-Infrared Instrument. It can detect thermal radiation, the heat signature emitted by planets and moons, and it has the resolution to distinguish between Pluto and Charon, something earlier telescopes couldn't do. The observations were made in two phases. First, in 2022, MIRI captured thermal light curves of both Pluto and Charon at wavelengths of 1821 and 25 micrometers. These measurements showed how the heat flux from each body changed as they rotated. Then, in May 2023, MIRI captured a high-quality spectrum of Pluto's atmosphere, covering wavelengths from 4.9 to 27 micrometers. This spectral range had never been explored before, because earlier instruments simply weren't sensitive enough. What the data revealed was unexpected. The JWST observations confirmed Zhang's prediction. Pluto's atmospheric haze is real, and it is emitting strong mid-infrared radiation, exactly as Zhang predicted in 2017. "We were really proud because it confirmed our prediction," Zhang said. In planetary science, it's not common to have a hypothesis confirmed so quickly, within just a few years. So, we feel pretty lucky and very excited. But the discovery goes deeper than just confirming a hypothesis. It reveals something fundamental about how Pluto's atmosphere works. On most planetary atmospheres, gas molecules control the energy balance. They absorb sunlight, they radiate heat, and they regulate the temperature. But on Pluto, it's the haze particles that dominate this process. The haze particles absorb sunlight and heat up. Then they radiate that heat away as infrared light. And because they're so effective at this, they cool the atmosphere significantly. The upper atmosphere of Pluto reaches temperatures around -203 degrees Celsius, or 70 Kelvin. Without the haze, models suggest it would be around -173 degrees Celsius, or 100 Kelvin. That's a 30-degree difference. The haze particles are made of organic compounds, hydrocarbon and nitrile ices that form when nitrogen and methane react in the upper atmosphere. These particles are tiny, just a few tens of nanometers across. But as they descend through the atmosphere, they collide and stick together, forming larger aggregates. Eventually, they settle onto the surface. This makes Pluto's atmosphere unique in the solar system. Its radiative energy balance is controlled primarily by haze particles, not by gas molecules. No other planet or moon works this way. But there's a paradox here, and it's one that scientists are still working to understand. The haze particles cool the atmosphere, but they also heat it. When the haze absorbs extreme ultraviolet light from the sun, it gains energy, and some of that energy is transferred to gas molecules in the atmosphere, heating them up. In fact, this heating is so effective that it gives molecules enough energy to escape from Pluto's atmosphere entirely. Pluto is losing 1.3 kilograms of methane to space every second. That's about 2.9 pounds per second, or roughly 112,000 tons per year. And about 2.5% of that methane is being intercepted by Charon, where it settles onto the moon's poles and gets chemically transformed by sunlight. This is what creates the reddish staining we see at Charon's polar regions. This phenomenon is unique. Nowhere else in our solar system do we see an atmosphere leaking onto a neighboring body. So how can the haze both heat the atmosphere and cool it? The answer comes down to particle properties. The size, shape, and composition of the haze particles determine whether they heat or cool the atmosphere. And these properties aren't fully understood yet. Cooling or heating depends on the haze properties, such as particle size, shape, and composition, said Tanguy Bertrand. We are currently investigating this with state-of-the-art microphysical models. What we do know is that the haze controls the balance of energy in Pluto's atmosphere. It affects global temperatures, atmospheric circulation, and what passes for climate on this frigid dwarf planet. And Pluto's climate is driven by cycles of sublimation and freezing. Nitrogen, methane, and carbon monoxide ice evaporate from the surface, move through the atmosphere, and then freeze out again in different locations. Much of this activity is centered around Sputnik Planitia, the heart-shaped feature on Pluto's surface. It's a deep basin filled with a glacier of nitrogen ice. Now, here's where it gets even more complicated. Pluto's orbit is highly elliptical. It takes 248 Earth years to complete one orbit around the Sun. And during that orbit, its distance from the Sun varies dramatically. At perihelion, Pluto is closer to the Sun than Neptune, at about 30 astronomical units. At aphelion, it's almost 50 astronomical units away. That's nearly twice the distance. This difference affects how much solar energy Pluto receives. And because the haze plays such a central role in the atmosphere's energy balance, the behavior of the haze changes with the seasons. Zhang described this in detail. Based on New Horizons temperature observations from 2015, we found that gas heating significantly exceeds gas cooling. So, there is a net radiative heating of the atmosphere. To maintain energy balance under these conditions, the haze must provide the necessary net radiative cooling. But Zhang added a caveat. It remains unclear whether haze has a net cooling effect during other seasons, as Pluto's seasons vary dramatically. This is important. The JWST observations captured Pluto at one specific moment in its orbit. But Pluto's atmosphere is constantly changing, and we don't yet know how the haze behaves over the full 248-year cycle. There's another complication. Pluto's atmosphere is expected to collapse eventually. Right now, the surface pressure is about 13 microbars. That's incredibly thin compared to Earth's 1 million microbars. But models predict that as Pluto moves further from the Sun, the atmosphere will cool and condense onto the surface. The pressure will drop, and the atmosphere may disappear entirely until Pluto swings back toward the Sun again. The question is when this will happen, and whether the haze will change the timeline. Now let's talk about what else JWST found. The mid-infrared spectrum captured by JWST revealed unexpected chemical richness in Pluto's atmosphere. The spectrum shows clear signatures of several gases produced by the photolysis of methane. When solar ultraviolet light breaks apart methane molecules, they recombine into more complex hydrocarbons. JWST detected ethane, acetylene, propyne, and diacetylene. All of these are products of methane photochemistry, and their presence confirms that Pluto's atmosphere is chemically active despite being so cold and thin. But there was something unexpected in the data. JWST detected fluorescent emission from methane and deuteromethane. Fluorescence means the molecules are emitting light at a higher energy than expected. It indicates that they're being excited by solar radiation in a way that doesn't involve collisions with other molecules. This is a process that's been observed in cometary atmospheres, but it's unusual to see it on a planetary body like Pluto. The detection of deuteromethane is particularly interesting. Deuterium is a heavy isotope of hydrogen, with 1 proton and 1 neutron in its nucleus. The ratio of deuterium to hydrogen, called the D-H ratio, is a marker of the origin and evolution of planetary materials. JWST measured Pluto's D-H ratio in acetylene. It found a value around 3 times higher than Earth's D-H ratio. This suggests that Pluto's ices formed in a very cold environment, possibly in the outer regions of the solar system, or even in the interstellar medium before the solar system formed. Cold environments favor the formation of deuterium-enriched molecules, but interpreting this ratio is difficult. The D-H ratio can change over time due to atmospheric escape, photochemistry, and other processes. So we can't say for certain where Pluto's ices came from based on this measurement alone. There's one more chemical finding worth mentioning. The JWST spectrum doesn't just show the atmosphere, it also shows the surface. At certain wavelengths, sunlight reflects off Pluto's surface before reaching the telescope, and in that reflected light, JWST detected absorption features from surface ices. Specifically, JWST detected methane, deuteromethane, and ethylene on the surface. This is consistent with what New Horizons observed in 2015. Pluto's surface is covered with patches of nitrogen, methane, and carbon monoxide ice. These ices sublimate and condense in seasonal cycles, redistributing across the surface over time. But the JWST data adds new detail. The detection of deuteromethane on the surface suggests that the D-H ratio we see in the atmosphere is also present in the surface ices. This makes sense, because the atmosphere and surface are in constant exchange. The detection of ethylene is more surprising. Ethylene is a product of methane photochemistry, so it forms in the atmosphere, but JWST detected it on the surface, which means it must be condensing out of the atmosphere and freezing onto the ground. This tells us that Pluto's atmosphere and surface are tightly coupled. What happens in one affects the other. Now, let's talk about the haze itself. The haze on Pluto is not made of water droplets or dust. It's made of organic particles. These particles form high in the atmosphere, where solar ultraviolet light breaks apart nitrogen and methane molecules. The fragments recombine into more complex hydrocarbons like ethane, acetylene, and benzene. And as these molecules collide, they stick together, forming tiny, solid particles. The JWST spectrum shows emission peaks from the haze at wavelengths of 15.45, 14.58, and possibly 13.6 micrometers. These peaks indicate the presence of specific molecules or molecular structures in the haze particles. The exact composition is still uncertain, but researchers believe the haze contains a mixture of pure and mixed ices. Possible candidates include diacetylene, benzene, and other complex hydrocarbons. What's clear is that Pluto's haze is very different from the haze on Titan. Titan's haze is made primarily of tholins, a class of organic molecules that form through nitrogen and methane chemistry. Pluto's haze contains similar compounds, but the spectral signatures are distinct. This difference likely comes down to temperature and pressure. Titan's atmosphere is much denser than Pluto's, and its surface temperature is warmer. These conditions favor the formation of different types of molecules. The haze particles on Pluto descend through the atmosphere over time. They agglomerate into larger aggregates as they fall. Eventually, they settle onto the surface, contributing to the reddish and brownish colors we see in some regions. This process connects the atmosphere to the surface. The haze particles carry organic material from the upper atmosphere down to the ground, where it accumulates over time. Now let's talk about what's happening on the surface. The JWST observations revealed variations in surface temperature across Pluto and Charon. MIRI captured thermal light curves at 4 wavelengths, 15, 18, 21, and 25 micrometers. These measurements showed how the heat flux from each body changed during their rotation. By comparing these light curves with thermal models, researchers were able to determine the thermal inertia, emissivity, and temperature of different regions. Thermal inertia is a measure of how quickly a material heats up and cools down. Regions with low thermal inertia, like fine dust, heat up quickly during the day and cool down quickly at night. Regions with high thermal inertia, like solid rock or ice, change temperature more slowly. On Pluto, the thermal inertia varies depending on the composition of the surface. Areas covered in methane ice have different thermal properties than areas covered in nitrogen ice or dark organic deposits. Emissivity is a measure of how efficiently a surface radiates heat. A perfect blackbody has an emissivity of 1. Most planetary surfaces have emissivities between 0.8 and 1. The JWST data showed that Pluto's emissivity varies across its surface. This makes sense, because different materials radiate heat differently. These properties drive the global ice distributions on Pluto. During the day, certain regions heat up more than others. This causes ice to sublimate from warm areas and condense in cooler areas. Over time, this process redistributes ice across the surface. The same process happens on Charon, but there's a key difference. Charon's polar regions are darker and redder than the rest of the surface. These regions have lower thermal inertia and higher temperatures during the day. The JWST data confirmed this. But the most interesting finding came from comparing the observations with models. The JWST data confirmed a second prediction, this one made by Linfeng Wan, a former PhD student of Zhejiang. In a 2023 study, Wan predicted the amplitude of Charon's rotational light curve based on thermal models. The JWST observations matched the prediction closely. This is important because it validates the thermal models being used to study the Pluto-Charon system. It shows that we understand, at least to some degree, how heat moves across the surfaces of these bodies. But it also raises a deeper question. Charon's polar regions are thought to be covered with organic material that originated on Pluto. Methane molecules escape from Pluto's atmosphere, drift through space, and get captured by Charon's gravity. They settle onto the poles, where they're chemically transformed by sunlight into more complex organic compounds. This process is unique in the solar system. Nowhere else do we see an atmosphere from one body depositing material onto another body. And the JWST data provides new insights into how this process works. The thermal properties of Charon's polar regions are consistent with a layer of organic soot covering water ice. This soot absorbs sunlight, heats up, and radiates heat away. It acts like a thermal blanket, insulating the ice below. The JWST observations also showed that the temperature of Charon's poles varies during rotation. This suggests that the thickness or composition of the organic layer varies across the poles. Understanding this process is important because it tells us how material moves through the Pluto-Charon system and it may have implications for other systems in the outer solar system. Pluto sits in a unique spot in the range of how planetary atmospheres behave. This gives us a chance to expand our understanding of how haze behaves in extreme environments, Zhang explained. And it's not just Pluto. We know that Neptune's moon Triton and Saturn's moon Titan also have similar nitrogen and hydrocarbon atmospheres full of haze particles, so we need to rethink their roles too. Triton is particularly interesting. It's thought to be a captured Kuiper belt object, similar in composition to Pluto. It has a thin nitrogen atmosphere and active geology, including geysers that erupt nitrogen gas. If Triton's atmosphere also has a haze that controls its energy balance, then the lessons we learn from Pluto could apply there as well. Titan's atmosphere is much denser than Pluto's, but it also has extensive haze. The haze on Titan is known to affect the atmosphere's energy balance, but the details are still being worked out. The JWST observations of Pluto provide a comparison point that could help refine our understanding of Titan. But Zhang sees an even deeper connection. Before oxygen built up in Earth's atmosphere, about 2.4 billion years ago, life already existed, he said. But back then, Earth's atmosphere was totally different. No oxygen, mostly nitrogen, and a lot of hydrocarbon chemistry. Early Earth's atmosphere may have been similar to Pluto's atmosphere today, dominated by nitrogen with methane and other hydrocarbons, and possibly containing a haze of organic particles. If that's the case, then studying Pluto's atmosphere could give us insights into the conditions that made early Earth habitable. The organic chemistry happening in Pluto's atmosphere is complex. Solar radiation drives reactions that produce increasingly complex molecules. These molecules rain down onto the surface, accumulating over time. On early Earth, similar processes may have contributed to the buildup of organic material that eventually led to the origin of life. This is speculative, of course. We don't know for certain that early Earth's atmosphere was similar to Pluto's, but the parallel is intriguing. Now, let's talk about what comes next. The JWST observations have answered some questions about Pluto, but they've raised many more. One of the biggest unknowns is how Pluto's atmosphere changes over its 248-year orbit. The JWST data captured a snapshot in time, but Pluto's distance from the Sun, and therefore the amount of solar energy it receives, varies dramatically over that orbit. As Pluto moves further from the Sun, the atmosphere is expected to cool and eventually collapse. But we don't know exactly when this will happen, and we don't know how the haze will behave as the atmosphere thins. Will the haze particles continue to form? Will they fall to the surface more quickly? Will the cooling effect of the haze accelerate the collapse or slow it down? These are open questions. Another unknown is the exact composition of the haze. The JWST spectrum shows emission peaks that indicate the presence of specific molecules, but interpreting those peaks is difficult. Different molecules and molecular structures can produce similar spectral features. Researchers are working on detailed models to match the observations, but it will take time to pin down the exact composition. There's also the question of how the haze affects Pluto's surface. The organic particles that settle onto the surface accumulate over time, but we don't know how quickly they accumulate or how they interact with the surface ices. Do they mix with the ices? Do they form a distinct layer on top? How do they affect the albedo and thermal properties of the surface? These details matter because they determine how Pluto's surface evolves over time. And then there's the question of Charon. The JWST observations have given us a new look at Pluto. But there's only so much a telescope can tell us from a distance of 5 billion kilometers. To answer the deeper questions, we need to go back. A concept mission called Persephone has been proposed. It would send an orbiter to the Pluto system, where it would spend 3 Earth years studying Pluto, Charon, and the smaller moons. The mission would launch in 2031 and arrive at Pluto in 2058 using a combination of radioisotope electric propulsion and a Jupiter gravity assist. Along the way, it would encounter 1 or 2 other Kuiper belt objects, giving us a broader look at this distant region of the solar system. Persephone would carry 11 instruments, high-resolution imagers and spectrometers to map the surfaces and atmospheres, a mass spectrometer to directly measure the composition of Pluto's atmosphere, an altimeter and radar sounder to probe the internal structure, a magnetometer and plasma spectrometer to study the magnetic field environment, One of the mission's primary goals is to determine whether Pluto has a subsurface ocean. The New Horizons data revealed features on Pluto's surface that suggest internal activity. Sputnik Planitia, the large nitrogen ice glacier, may have formed from an ancient impact. But if it did, then Pluto should have reoriented itself over time to place the basin near the equator. This reorientation would require the basin to be a positive gravity anomaly, which could be explained by a subsurface ocean. But we don't know for certain. The only way to find out is to measure Pluto's gravity field with an orbiter. Persephone would do this using radio science. By tracking the spacecraft's motion as it orbits Pluto, researchers could map the gravity field and determine the internal structure. If a subsurface ocean exists, it would show up as a gravity anomaly beneath Sputnik Planitia. The mission would also study Pluto's atmosphere in much greater detail than JWST can provide. A mass spectrometer could directly measure the composition of the atmosphere, including trace species that are difficult to detect remotely. And by orbiting Pluto for 3 years, Persephone could monitor changes in the atmosphere and surface over time. It could watch the seasonal cycles of ice redistribution. It could measure the rate of atmospheric escape. It could track how the haze behaves as Pluto's distance from the Sun changes. But Persephone is still just a concept. It hasn't been approved for development. And even if it were approved today, it wouldn't arrive at Pluto until 2058. That's 33 years from now. The thermal light curves captured by JWST's MIRI instrument revealed something unexpected about how heat moves across Pluto's surface. When a planetary body rotates, different regions face the Sun at different times. The sunlit side heats up, the dark side cools down. And by measuring how the thermal emission changes during rotation, scientists can learn about the thermal properties of the surface. On Pluto, the light curves showed variations that didn't quite match the predictions. Some regions heated up faster than expected, others stayed cooler longer. And the patterns were different at different wavelengths, suggesting that the surface composition varies in complex ways. The measurements were taken at 15, 18, 21, and 25 micrometers. Each wavelength probes a slightly different depth into the surface. Shorter wavelengths sample the top layer, longer wavelengths penetrate deeper. By comparing the light curves at different wavelengths, researchers could determine how the thermal properties change with depth. And what they found suggests a layered structure in some regions. For example, areas covered in methane ice show different thermal behavior than areas covered in nitrogen ice. Methane ice is more reflective and has lower thermal inertia. It heats up quickly during the day and cools down quickly at night. Nitrogen ice, on the other hand, has higher thermal inertia. It changes temperature more slowly. This makes sense because nitrogen ice is denser and conducts heat more efficiently. But there are also regions that don't fit neatly into either category, regions where the thermal behavior suggests a mixture of materials or perhaps a layer of dark organic material covering brighter ice underneath. These dark deposits are thought to be tholins, the organic particles that rain down from the atmosphere. Over time, they accumulate on the surface, forming a layer that affects how the surface absorbs and radiates heat. The thickness of this layer varies across Pluto. In some areas, it may be just a few centimeters thick. In others, it could be meters thick. And this variation affects the thermal light curves in ways that are difficult to model. Understanding these patterns is important because they tell us how material moves across Pluto's surface over time, and they provide clues about the history of different regions. Now let's talk about Sputnik Planitia. Sputnik Planitia is the most distinctive feature on Pluto's surface. It's a massive basin filled with nitrogen ice, shaped like the left half of a heart. The basin is about 1,000 kilometers across and several kilometers deep, and it sits almost exactly on Pluto's equator, directly opposite the anti-Charon point. This position is not random. It's the result of a process called true polar wander, where a planet or moon reorients itself so that a mass anomaly ends up at a specific location. In Pluto's case, the reorientation would have been driven by tidal forces from Charon. But for this to happen, Sputnik Planitia would need to be heavier than the surrounding terrain, despite being a depression. How can a basin be heavier than the terrain around it? One explanation is that the basin is filled with nitrogen ice that's thicker than the crust it replaced. But calculations show that the ice alone isn't heavy enough to explain the reorientation. Another explanation is that there's a subsurface ocean beneath Sputnik Planitia. If the impact that created the basin thinned the ice shell, then a liquid ocean underneath would bulge upward, creating the necessary mass anomaly. This explanation requires Pluto to have a subsurface ocean, and maintaining such an ocean on a body as small and cold as Pluto is challenging. The heat would need to come from radioactive decay in Pluto's rocky core, and the ocean would need to be insulated by a layer of clathrate hydrates, a type of ice that traps gas molecules in its structure and has very low thermal conductivity. The JWST observations don't directly address this question, but they do provide new constraints on the thermal properties of the surface around Sputnik Planitia, which could help refine the models. What the observations show is that the thermal emission from Sputnik Planitia is different from other regions. The nitrogen ice has distinct thermal properties that make it stand out in the light curves. And there's another feature of Sputnik Planitia that's worth discussing. The nitrogen ice in Sputnik Planitia is not static, it's convecting. Convection is a process where warmer material rises and cooler material sinks, creating a circulation pattern. On Pluto, this happens because the nitrogen ice at the bottom of the basin is slightly warmer than the ice at the surface. The heat comes from Pluto's interior. As it flows upward, it warms the base of the ice layer. The warm ice becomes less dense and rises. When it reaches the surface, it cools, becomes denser, and sinks back down. This creates a pattern of cells across Sputnik Planitia. Each cell is roughly 20 to 30 kilometers across, separated by troughs where the ice is sinking. The New Horizons images showed these cells clearly, and they revealed something surprising. The cells are moving. By comparing images taken at different times during the flyby, researchers estimated that the convection cycles take about 500,000 years to complete. That's fast, geologically speaking. It suggests that heat is flowing from Pluto's interior at a relatively high rate. But here's the question. Is the convection still happening today? The New Horizons flyby was in 2015. The JWST observations were in 2022 and 2023. That's only 7 to 8 years later. Not enough time to see significant changes in the convection pattern. But by the time the Persephone mission arrives in 2058, 43 years will have passed since New Horizons. That might be enough time to detect changes, if the convection is happening as fast as the models suggest. If Persephone does detect changes, it would provide direct evidence that Pluto is still geologically active, and it would constrain the heat flow from the interior, which would help determine whether a subsurface ocean exists. But that's decades away. For now, we can only infer the convection from the patterns we see frozen in time. Now let's talk about the composition measurements. The mid-infrared spectrum captured by JWST contains a wealth of information about Pluto's atmosphere and surface. But extracting that information is not straightforward. The spectrum is a superposition of multiple components. There's reflected sunlight from the surface. There's thermal emission from the surface. There's thermal emission from the atmosphere. And there's emission from the haze. Each component contributes to the spectrum at different wavelengths, and separating them requires careful modeling. Researchers used radiative transfer codes to model how light moves through Pluto's atmosphere. They started with vertical profiles of gas concentrations from photochemical models. These models predict how methane photochemistry produces ethane, acetylene, and other hydrocarbons at different altitudes. Then they calculated how these gases absorb and emit radiation at different wavelengths, and they compared the results to the JWST spectrum. The fit was good, but not perfect. The ethane abundance matched the photochemical models very well. This was reassuring because it suggested the models are capturing the basic chemistry correctly. But propyne and diacetylene were lower than predicted. Propyne was about 5 times lower. Diacetylene was about 10 times lower. Why the discrepancy? One possibility is that the photochemical models are overestimating the production rates of these molecules. The models rely on laboratory measurements of reaction rates, and those measurements have uncertainties. Another possibility is that the vertical profiles are different from what the models predict. The molecules might be concentrated at different altitudes, which would change their spectral signatures. There's also the possibility of non-thermal effects. The acetylene emission band between 12.9 and 14.7 micrometers didn't fit perfectly. This could indicate that the acetylene molecules are not in thermal equilibrium. They might be excited by solar radiation in ways that aren't captured by the models. Understanding these discrepancies is important because it affects our interpretation of the chemistry. If the models are wrong, then we need to revise them, and that could change our understanding of how Pluto's atmosphere evolved over time. There's one more molecule worth discussing. Hydrogen cyanide was tentatively detected in the JWST spectrum. Hydrogen cyanide, or HCN, is a molecule made of one hydrogen atom, one carbon atom, and one nitrogen atom. It's a product of nitrogen and methane photochemistry, and it's been detected in the atmospheres of Titan and several comets. On Pluto, HCN is expected to form in the upper atmosphere, where solar ultraviolet light breaks apart nitrogen and methane molecules. The fragments can recombine to form HCN. The detection is tentative because the spectral signature is weak and overlaps with other features. But if confirmed, it would be the first direct detection of HCN in Pluto's atmosphere. HCN is interesting for several reasons. First, it's a key intermediate in the production of more complex organic molecules. It can react with other molecules to form amino acids, nucleotide bases, and other prebiotic compounds. These are the building blocks of life. Second, HCN is volatile. It sublimates at relatively low temperatures, which means it can move between the atmosphere and the surface. If HCN is condensing onto the surface, it could be accumulating in cold traps, similar to water ice in the permanently shadowed craters on the Moon. Third, the abundance of HCN depends on the nitrogen to carbon ratio in the atmosphere. Measuring HCN could help constrain this ratio, which would provide insights into the origin of Pluto's volatiles. Did Pluto's nitrogen and carbon come from the same source? Or did they come from different sources and mix together later? These are fundamental questions about how Pluto formed, and HCN could provide part of the answer. But confirming the detection will require more observations. JWST could observe Pluto again at a different time in its orbit, when the atmospheric conditions are different. That would help distinguish the HCN signal from other features in the spectrum. Or we could wait for the Persephone mission, which would carry a mass spectrometer capable of directly measuring HCN in the atmosphere. Now let's talk about the upper limits. The JWST spectrum also provided upper limits on several molecules that were not detected. These include ethylene, propane, benzene, cyanoacetylene, and carbon dioxide. Upper limits are useful because they constrain the chemistry. If a molecule is expected to be present but isn't detected, it tells us something about the processes that produce or destroy it. Take ethylene, for example. Ethylene is a product of methane photochemistry, and it should be present in Pluto's atmosphere. But the JWST spectrum didn't show a clear detection. This could mean that ethylene is present at lower concentrations than expected. Or it could mean that ethylene is being converted into other molecules faster than it's being produced. Benzene is another interesting case. Benzene is a ring-shaped molecule made of 6 carbon atoms and 6 hydrogen atoms. It's a common product of hydrocarbon chemistry, and it's been detected in Titan's atmosphere. On Pluto, benzene is expected to form through reactions involving acetylene and other small hydrocarbons. But again, JWST didn't detect it. One possible explanation is that benzene is condensing out of the atmosphere and freezing onto the haze particles. If that's the case, then benzene might be a major component of the haze, even though it's not detectable in the gas phase. This is consistent with the haze emission spectrum, which shows features that could be explained by icy particles containing benzene or other complex hydrocarbons. Carbon dioxide is an interesting non-detection as well. Carbon dioxide has been detected on Pluto's surface by ground-based observations, but it wasn't detected in the atmosphere by JWST. This suggests that carbon dioxide is not sublimating significantly at the time of the observations. It's locked in the surface ice, not contributing to the atmosphere. This makes sense given Pluto's temperature. Carbon dioxide has a higher sublimation temperature than nitrogen or methane, so it would stay frozen when those other ices are evaporating. These upper limits help refine the photochemical models. By knowing what's not present, or present in only small amounts, researchers can adjust the models to match the observations more closely. And that brings us to the comparison with other worlds. Pluto's atmosphere has often been compared to Titan's atmosphere. Both are dominated by nitrogen. Both contain methane. Both have extensive hazes formed by photochemistry. But the JWST observations highlight important differences. Titan's atmosphere is much denser than Pluto's. The surface pressure on Titan is 1.5 bars, about 50% higher than Earth's surface pressure. Pluto's surface pressure is only 13 microbars. This difference affects the chemistry. On Titan, molecules collide frequently, which drives certain types of reactions. On Pluto, collisions are much rarer, so different reactions dominate. The haze composition is also different. Titan's haze is rich in nitrogen-bearing organics, including nitriles and nitrogen heterocycles. Pluto's haze appears to be richer in hydrocarbon ices. The JWST spectrum showed clear differences in the haze emission features. Pluto's haze has peaks at wavelengths that don't match Titan's haze. This suggests that the molecular structures are different, even if the overall chemistry is similar. Temperature also plays a role. Titan's surface temperature is around 94 Kelvin. Pluto's surface temperature ranges from 35 to 55 Kelvin, depending on location and season. This 40 to 60 Kelvin difference affects which molecules can exist as gases and which condense into solids. On Titan, many organic molecules remain in the gas phase all the way down to the surface. On Pluto, those same molecules would freeze out at high altitudes, contributing to the haze instead. Despite these differences, studying Pluto helps us understand Titan. The two worlds represent different regimes of nitrogen-methane photochemistry. By comparing them, we can identify which processes are universal and which depend on specific conditions. And this comparison extends beyond our solar system. Exoplanets with nitrogen-rich atmospheres and hydrocarbon hazes may exist around other stars. Understanding how such atmospheres work is important for interpreting observations of those distant worlds. Pluto is a laboratory that's within our reach, a place where we can test our theories and refine our understanding. And the lessons we learn here will inform our exploration of worlds we may never visit in person. But there's one more connection worth exploring: the connection to Earth. Before oxygen became abundant in Earth's atmosphere, our planet may have looked very different from the sky. About 2.4 billion years ago, Earth underwent a transformation called the Great Oxidation Event. Photosynthetic organisms began producing oxygen as a waste product, and over time, oxygen built up in the atmosphere. But before that happened, Earth's atmosphere was reducing rather than oxidizing. It was dominated by nitrogen, with smaller amounts of methane, carbon dioxide, and other gases. Some researchers believe that early Earth may have had a haze layer, similar to the hazes we see on Pluto and Titan today. This haze would have formed through photochemistry. Solar ultraviolet light would break apart methane molecules in the upper atmosphere, and the fragments would recombine into more complex hydrocarbons. These would form tiny particles that scattered sunlight, creating a haze. If early Earth did have such a haze, it would have affected the climate. The haze would have absorbed ultraviolet light, protecting the surface from harmful radiation. But it would also have scattered visible light, cooling the surface. This creates a paradox. Early Earth needed to be warm enough for liquid water to exist on the surface, but a thick haze would have a cooling effect. How could Earth have stayed warm? The answer might involve the balance between heating and cooling, similar to what we see on Pluto. If the haze absorbed enough ultraviolet light, it could heat the upper atmosphere while cooling the lower atmosphere and surface. The net effect would depend on the properties of the haze particles. By studying Pluto's haze in detail, we can learn how organic hazes behave in nitrogen-rich atmospheres, and that knowledge can inform our models of early Earth. There's also a connection to the origin of life. The organic molecules produced in Pluto's atmosphere are similar to the molecules that may have contributed to the origin of life on Earth. Amino acids, nucleotide bases, and other prebiotic compounds can form through reactions involving nitrogen, methane, and other simple gases. On Pluto, these molecules freeze and fall to the surface. On early Earth, they may have dissolved in the oceans, where they could participate in more complex chemistry. Studying Pluto's organic chemistry gives us a window into the types of molecules that might have been present on early Earth. And that helps us understand the chemical pathways that led from simple gases to the first living organisms. This is speculative, of course. We don't have direct evidence of what early Earth's atmosphere was like, and we don't know for certain that it had a haze. But the parallels are compelling, and the more we learn about Pluto, the more we realize that this distant, frozen world may have something to teach us about our own planet's past. The universe has a way of connecting things in unexpected ways. A dwarf planet at the edge of the solar system, a moon orbiting Saturn, and a rocky planet in the habitable zone of its star billions of years ago. They're all part of the same story, the story of how chemistry creates complexity, how simple molecules become complex molecules, and how complexity, given enough time and the right conditions, can lead to life. Pluto is just one chapter in that story, but it's a chapter worth reading.